I want to talk about an interesting example you might run into. And I'm going to talk about it in terms of the circuit that you see just aside of me. It's basically an interesting circuit. It's a circuit where I've got two capacitors, a voltage-controlled current source, and that's it. And you look at this and you imagine if you saw this. For example, you're taking an exam and this is a problem that shows up. You probably think, what do I do with this problem? The first thing you might think is I got two capacitors here in series, I could combine them, but I do kind of need this voltage. And I don't really have a place to do a capacitive voltage divider, so, I really have to actually think about this. So what do I do about a circuit like this? And so that's part of the conversation we're going to want to do. And because you could immediately start by saying, well, let me try to write something like, KCL, at each of these nodes, and I would find that I would get some equation equals to another equation in other ones, because of course it's the same current going through here. Remember, the current is not actually going through the insulator. It's the current between here and this plate is here to here, and so on. That being said, you would get these two equations. You would get this next equation out of that, just simplifying, putting in Laplace. You could take two pieces of it and then write down two separate equations. And you'd think, okay, this is a lot of stuff. And so how do I begin to think about this problem? Where does it come from and how do I begin to look at it? Well, let's kind of step back a second. One of the ways to think about sort of voltage-controlled current sources and capacitors is thinking back to what you might see in op-amp circuits. Because although we talk about op-amps as effectively being, basically, infinite sort of gain structures, really what they're probably best known for is really being integrators. But that's probably a little bit different way of approaching this. But one of the classic circuits you might imagine is taking an op-amp type circuit with capacitive feedback. There are ways to do this, particularly if you have a CMOS process. You can have transistors that basically make all of this look perfectly as you would expect to draw this. And so you could actually look at this circuit and go, okay, there's no current in here, there's no issue. So basically I would say that I could just say, write down this equation below, C equals that, equals a minus C out. And I find out the output voltage is C1 over C2 times Vn, which just makes sense because it's an inverting amplifier. You might go, well, this feels like what I would expect. In particular, if I could do Laplace, that would be what I'd expect, except that I have an offset here, right? Because if I were to do this as Laplace and look at the two impedances, I'd say, well, this would be SC1 over SC2. But remember, I can't divide when S is equal to 0. What is S equal to 0? That's DC. That means there's an offset in there, but it runs all the way to DC. So even if I were to put a step function, like a nice heaviside step function in there, I'm going to actually see this is going to be the main expression. This is going to be true all the way down to zero frequency, and there's just an offset in place. So there's some sort of sense of having a gain of an amplifier like this, and I could make an argument of here's a C1 and a C2. Look how this is being structured, and think about having a current source where its sort of integration structure is coming from C2. So there's an interesting similarity here. If you work through the math and you say, let me take these two things and equate them, which basically the way you would do that is you would multiply them so that way you kind of keep everything sort of in numerator form. You try to be careful and not have too many embedded fractions, otherwise you're going to end up getting stuff that gets just more and more complicated, and the chance of making errors just keeps growing. But what you can then do is you get to this expression, which looks a little bit better but looks a little messy, and you're like, I've got a bunch of 2 second order S's on both sides, and you're thinking this must be a second order system, and your intuition is going, but that's weird, there's only one state variable, where are we going with this? Hold on for a moment. And what you find is that I get, S over S, C1, C2, minus what is effectively a 0 in the numerator and a pole in the denominator. This is the sort of the main integration term. And you look at this and you think, okay, I think this is a first order transfer function. In fact, I should just be able to divide through the S's, right? No problem. Except remember, I can't do it at s equals 0. So I do have an offset term much like I have here, and I've kind of spared like trying to invert this out from a step response, but it's, again, kind of what you would expect. Looking at any other sort of first order circuit, you can get some very similar structure. Now notice you have something that says what's the gain, and the gain is going to be sort of the main sort of low frequency gain. And then I'm going to get a time constant, C1 over GM is going to be the first order time constant. So for the most part, this looks like a first order system with a 0 here that basically says, okay, as I get to fairly higher frequencies, it's going to look like I'm going to go input to output and pass all the way through. And notice that when S is large, it's just going to be these two terms. The minus signs will disappear, and I'm going to get a sub v divided by a sub v, which gives me 1. So I'm going to basically just be passing the signal through. This is called feed through, a very common thing that happens with sort of capacitive type networks at the higher frequency ranges. And so what you can see is you can take what looks like a rather strange looking circuit at first, and it turns out it's really not that complicated, but it's important to kind of have intuition, and this is why we talk about having simpler circuits like this to kind of guide our intuition when we try to look at something a little bit more complicated, because in fact a circuit like this comes from asking questions like the first one.